So yeah, good evening everyone. I hope I'm audible and visible. So let's wait 5 to 10 minutes so that everyone can join this session. So okay, let's start the session. Good evening everyone and warm welcome to all of you. I hope I'm audible and visible. Can anyone confirm me? So yeah, my name is Pooja Verma. I'm PMRF Research Scholar from IIT Kharagpur, and the instructor for this course is Professor Shyamal Das Mandal, Advanced Technology Development Center, IIT Kharagpur. This is a week 8 live interactive session of signal processing techniques and its applications. So I hope all of you have gone through this week video content. So we will start uh, from some theoretical concepts and formulas, then we will move to the some assignment problems. Okay, so for this week, the study have been done on digital filters and design specifications of digital filters. So what are the main requirements for design a digital filter or any filter? So this is the frequency response of a low pass filter. So to design any filter, the main parameters are required, that is pass band frequency, stop band frequency, peak ripple in the pass band, stop band ripple, and normalized transition bandwidth. So in this figure, this is a pass band ripple, and this one is a pass band frequency, and this one is a stop band frequency, and the difference between the stop band frequency and pass band frequency is called transition bandwidth or bandwidth, and this is called where the stop band frequency start. It is called stop band ripple. Okay, so design any filter. The these are the main parameters which are required. Okay, next, in the pass band, the frequency is 0 to omega p. Already you have seen that in the frequency. This is a stop pass band frequency. So it varies from 0 to omega p. And what are the stop band frequencies? Stop band frequency varies from omega s to pi. Okay, this is the frequency. And this is a magnitude of a low pass filter. So the magnitude of a pass band varies from 1 minus del p to 1 plus del p. And similarly, the stop band magnitude or ripple can vary del s plus minus del s minus del s to del s, or 0 to del s. Okay, peak pass band ripple represented as a alpha p, that is equal to minus 20 log 10 1 minus del p in the dV. Similarly, the minimum stop band attenuation required is minus 20 log 10 del s dV. Okay. Now what is a FIR filter? FIR states a finite impulse response. A finite impulse response filter is a discrete linear time invariant system whose output is based on the weighted summation of finite number of past inputs. So it is represented as h of z is equal to summation n varies 0 to n capital N h of n z to the power minus n. Here n represents the finite number. So that is why it is called a finite impulse response. The impulse response is required to be a linear phase. The filter coefficient must satisfy the constant. So the FIR filter must satisfy the linearity property, or linear, it must be a linear phase. So h of n is equal to plus minus h n minus of n, capital N minus of n. For symmetric unit sample response of h of n, the number of filters coefficients that specify the frequency response is m plus 1 by 2 when m is odd, and m by 2 when m is even. So it must be learned for symmetric unit sample. Okay. So if someone asks to the filter coefficient, so when m is odd, then the number of frequency filter coefficient must be m plus 1 divided by 2, and when m is even, then m by 2. And if unit sample response is antisymmetric, then number of filter coefficients are m minus 1 divided by 2 when m is odd, and m by 2 when m is even. Okay. Now, what are the common approaches to design a FIR filter? So there are three methods to design a FIR filter. That first one is a window Fourier series approach. Another one is frequency sampling approach, and another one is a computer-based optimization method. So for window Fourier series approach, here we are selecting any of the window depends on the design specifications, and then this window function must be multiplied by the impulse response in order to get the FIR filter or design specification or different parameters of a FIR filter. So what are the different types of window functions are available? There are different types of window functions are available, that is rectangular window, Bartlett, Hanning, Hamming, Blackman, Kaiser window, and all other types of window functions are available, and their approximate transition width is also specified, and their peak side lobes are defined in this table. So for rectangular window, the transition bandwidth is 4 pi by m. Okay, and Bartlett, Hamming, and Hanning window, for these three window function, the transition bandwidth is 8 pi by m, and for Blackman window, the transition bandwidth is 12 pi by m. It is this is required while we are solving the question or assignment problems. So please remember these points. And about the peak side lobes also. For rectangular window, the peak side lobe is minus 13 dB. For Bartlett window function, the peak side lobe is minus 27 dB. For Hanning window, minus 32 dB, and for Hamming window, minus 43 dB, and for Blackman window, the peak side lobe is minus 58 dB. The another approach for design FIR filter is frequency sampling approach. So in the frequency sampling approach, there are two types, type 1 or type 2. In type 1, there is also when n is even and n is odd. So when n is even, then you can see this is a Z transform of the impulse response. So already you have gone through this, I think, this diagram. This is a ROC of the Z transform. So when n is even, then the points must be asymmetrical through this axis, real and imaginary axis. And when n is odd, then the points are not symmetrical. You can see that the number of points here 3, here 2, 2, then 3, 2 here. So when n is odd, the one point must be at this point. Okay, for type 1, f is equal to 2 pi k n or k fs by n. For k is equal to 0 and f is equal to 0. And for type 2, when n is even, then the difference between type 1 type 2, here in the type 1, we will start from this point, and when type 2, I hope all of you have gone through that video lectures and the respective equations of type 1 and type 2. From there we will get these frequency sampling methods, type 1 and type 2, for symmetric and antisymmetric functions. For type 2, if n is even, then it will start not from this point, it will start from this in order to make a symmetric function. And when n is odd, then it must be one point at this point. So the f will be get 2 pi by n k plus 1 by 2 or k plus 1 by 2 fs divided by n. For k is equal to 0, f is equal to fs by 2n. For symmetric, in order to get the impulse response of a function or design a filter, the value of gk we can get from here for alpha is equal to 0 and for alpha is equal to 1 by 2. For alpha is equal to 0, this formula has been applied, and for alpha is equal to 1 by 2, then this formula must be applied, and this is useful when we are solving the question. So g of k is equal to minus 1 to the power k hr 2 pi k by n, and gk must be minus g of n minus k. And in order to get h of n or impulse response of function, it is defined by this equation: 1 by n g of 0 plus 2 k varies 0 to u gk cos 2 pi k n plus 1 by 2, and u we are get from here when n is odd n minus 1 varied by 2, and when n is even n by 2 minus n minus 1. And when alpha is equal to 1 by 2 is given, then we must be applied this formula. For alpha 1 by 2 g k plus 1 by 2 is equal to minus 1 to the power k hr 2 pi k 1 by 2 k plus 1 by 2 divided by n. Gk plus 1 by 2 must be equal to minus g n minus k minus 1 by 2 in order to ensure the linear phase. And h of n we get from 2 by n summation k is equal to 0 to u g k plus 1 by 2 sin 2 pi n k plus 1 by 2 n plus 1 by 2, and you will get same when n is odd n minus 1 by 2, and when n is even n by 2 minus 1. And similarly for antisymmetric filter, when alpha is equal to 0 and alpha is equal to 1 by 2. So for alpha is equal to 0, gk we will get from this one minus 1 to the power k hr 2 pi k by n, and g of k must be equal to minus g n minus k, and h of n we will get from here when n is odd, so h of n is equal to 2 by n summation k is equal to 0 to n minus 1 by 2 gk sin 2 pi k by n plus 1 by 2, and when n is even, then we will get h of n from this one 1 by n in bracket minus 1 to the power n plus 1 g n by 2 minus 2 summation k varies 0 to n by 2 minus 1 gk sin 2 pi k by n in brackets n plus small n plus 1 by 2. And for alpha is equal to 1 by 2 is given, then g of k plus 1 by 2 is equal to minus 1 to the power k hr 2 pi k plus 1 by 2 divided by n, and g of k plus 1 by 2 must be equal to minus g n minus k minus 1 by 2. And here if g n by 2 is equal to 0 for n is odd in this equation, and h of n we will get from 2 by n, k varies from 0 to u or v, you can take here u, g in brackets k plus 1 by 2 cos 2 pi by n k plus 1 by 2 n plus 1 by 2, and similarly u varies, we can find out u from here if n is odd n minus 1 divided by 2, and if n is even, then n by 2 minus of n 1. So let's move to the assignment question. So the first question is, if h of z is the z transform of the impulse response of an FIR filter, then which of the following relation is true? Option A, z to the power m plus 1 h z inverse is equal to plus minus h of z. Option B is z to the power minus m plus 1 h z inverse is equal to plus minus h of z, and option C is z to the power minus in brackets m minus 1 h of z inverse is equal to plus minus h of z, and option D is z to the power m minus 1 z h of z inverse is equal to plus minus h of z. So how to solve this question, or what if you want to try for this question, what is the correct answer for this question? If h of z is a z transform of the impulse response of an FIR filter, then which of the following relation is true? So, okay. As we know that the impulse response of an FIR filter is represented as h of z is equal to c is equal to 0 to n or m minus l. It is m minus 1 is given. So m minus 1 h of k z to the power minus k minus k. And we also know that h of n must be a linear phase. H of m minus 1 minus n, right? Where n is varies from 0, 1, 2 to m minus 1, right? Then we need to apply this symmetric or antisymmetric condition on this, and first substitute z inverse in terms of z inverse in place of z, then multiply both sides z to the power minus m minus 1. Okay, then in this equation we need to apply these parameters. So first we need to take the z transform of this. So what we will get, h of z is equal to plus minus, what we will get, z to the power m minus 1 h of z, right? Or minus, because if we take z to the power minus h of n, in order to change, then we will here. So if we first change this z to z inverse, then it will be with a z inverse, and here we will get z m minus 1, or z inverse minus will be cancelled, h of z inverse, then multiply with this z to the power minus m minus 1. So from this side we will get z to the power minus m in bracket minus m minus 1 h of z inverse equal to, then this minus and plus will be, this part will be cancelled, then and h of z, right? Z inverse. So this is correct answer is option C. Okay, okay, in this it is a h of z only. So the correct option we will get here at option C. Okay, and I hope already you have been solved this question in the video also. So have you got this question? Okay, so can we move to the next question? Okay, moving to the next question. So second question is, what is the value of h m minus 1 divided by 2 if unit sample response is antisymmetric, when m is odd. So it is given the unit sample response is antisymmetric, that is not a symmetric, and the m is odd. So what will be the value of m minus 1 divided by 2? So as we know that for linear phase FIR filter must be a linear phase function, so h of n is equal to minus h m minus 1 minus n. And m is odd, it is also given, m is odd and unit sample response is antisymmetric. So for m is equal to odd, the center point of the antisymmetric function n is equal to m minus 1 divided by 2. So consequently, h of m minus 1 divided by 2 must be 0. Or you can take any example. If m is odd, that means number of samples will be 3, 5 or 4. 3, 5, 7, 9, right? So let's take 3 samples, 0, 1, 2. So you know that is h of 0, right? And these are must be h of that if we will take h of 0 must be equal to this, these will be the equal and this is, so at the midpoint h of m minus 1 by 2 must be a 0. Okay, so the correct answer is option A. So when there is a no signal is given, here we need to take a simple unit sample response. So for antisymmetric function, the unit sample response when m is odd is 0. Okay. Okay, so moving to the next question. A low-pass digital FIR filter is designed using the following specifications. So transition bandwidth is given 200 Hz, cutoff frequency is 4 kHz is given, sampling frequency of the input signal is 10 kHz, and the filter is implemented using the rectangular window. Determine the order of the FIR filter. Here the transition bandwidth is given. The transition bandwidth is represented as del of omega. You have seen in the first slide. So transition bandwidth is given 200 Hz and sampling frequency FS is given 10 kHz, and it is given that the filter is implemented using the rectangular window. So what is a transition bandwidth for a rectangular window? You have seen in the previous slide, it is a transition bandwidth that is 4 pi by m, right? Okay, so 4 pi by m. Here, in order to determine, this is the order of the FIR filter, m is represented as order of FIR filter. So transition bandwidth is given, that is 200 Hz, right? And you know that this can be divided to multiplied by 2 pi, right? Divided by m. This can be written as, here 2, what is represented as a 2 pi. 2 pi is nothing but a sampling frequency. Any frequency is repeated after 2 pi, so 2 pi represents the sampling frequency. So 200 Hz equal to 2 multiplied by 10 kHz, sampling frequency is given as 10 kHz divided by m. So m, from here we will get 20 into 10 to the power 3 divided by 200 Hz. So this will be cancelled to 100. So the order of the filter is 100. Right? Have you got this question? Here 2 pi is equal to Fs. So here we will write in place of 2 pi, that is Fs. Fs is 10 kilohertz is given. So you can find it like this. Okay. So have you got this question? Can we move to the next question? Okay. Okay. Moving to the next question. Okay. So if the order of the filter as described in question number 3 is double, here how much we get order? Order is, we have get 100, right? In the previous question, what we get? 100 order of the filter is double and designed using the Hamming window. Then what will be the transition bandwidth? So now we need to design with a Hamming window. We need to design a filter with Hamming window. So what is the transition bandwidth for Hamming window? That is given in that table. So transition bandwidth is represented as del of the Hamming window. For Hamming window, it is 8 pi by m. Okay, so we need to find out the transition bandwidth of the Hamming window. So how we can write it? 4 into 2 pi, and 2 pi represents the sampling frequency. 4 into 2 pi by m. Here m we got 100, so here the order of the filter is double. So now m will be 200 if we take a double, and 4 into 10 kilohertz divided by 200. So what will we get? 400 into 10 to the power 2. So 200. Again, the transition bandwidth for Hamming window is 200 hertz only. Okay. So have you got this? I hope all of you got this question. Okay. Moving to the next question then. Let unit sample response of a filter is satisfied the equation 1. That is the equation 1. As we also know that the FIR filter must be a linear phase. So as below, if n is odd, then which of the following linear phase FIR filter cannot be designed? Here it is given n is odd, then which of the following FIR filter cannot be designed with this function? Option A is low pass, option B is high pass, option C is band pass, or option D is band pass. It is given that h of n must be equal to minus h n minus 1 minus n here. If we take a Z transform, or if we put n is equal to 0 and at n is equal to finite, or if we find out h of omega, that then at n is odd, then as you know that for n is odd at this point it will be the 0 also, and other thing, if we put h of 0, then we will get 0 only, and at the end frequency h of pi, it is also we will get 0. So this is not suitable as either low pass or high pass filter. So for this function, we cannot design a low pass or high pass filter. So correct is option is 1 and 2 both. So if a filter or impulse response is linear phase h of and n is odd, then we cannot design a low pass or high pass filter. Okay. Okay. Moving to the next question. H of n is a real valued linear phase finite length filter if 6 plus 8j is 0, the filter then which of the following are also a zero of the filter? It is a zeros of the filter. Think. Here h of n is given real valued linear phase finite length filter. It is a finite length. And if 6 plus 8j is a zero of the filter, then which of the following other other coefficient of the filter? So 6 plus 8j is a complex. The complex of 6 plus 8j is, so there must be a 6 minus 8j also. So what are the other parameters that can we take? Here we need to assume, or we need to take the assumptions from the, if any question is given like this, one zeros of a filter coefficients are given, then what are the other coefficients must be? So if it is a complex or in this form 6 is real plus imaginary, so the conjugate part must be there, 6 plus 8j or 6 minus 8j. Similarly, the any combination of this type of, or if that can equal the, if we multiply or add in, or multiply or division we can take, that must be equal in both. So that can be 6 minus 8j or 0.6 minus 0.8j, 0.6 plus 0.8j. Okay. So if one is given, then conjugate of the other, conjugate of this coefficient and multiplication or division or any number or factor, that is must be following the conjugate symmetricity property. So 6 minus 8j, 0.6 minus 0.8j or 0.6 plus 0.8j. Okay. Here the other options are wrong because that is 8 minus 6j, that is not, if you multiply we will get a different answer. Here you have to just concentrate the options in this type of questions. Okay. Sorry. I think you have got that question. We can move to the next question. Okay. The next question is, determine the value of h of 0, h of 1, h of 5 and h of 4 of a linear phase FIR filter of length m is equal to 6, which has symmetric unit sample response and a frequency response that satisfies the condition as in equation 2. Okay, here it is given, we need to determine the values of h of 0, h of 1, 5, h of 5 and h of 4. It is a linear phase and m is also given. M is given, this is a event. Okay, and it is also given, it has a symmetric unit sample response and satisfies the equation. So how we will get that h of 0, h of 1, h of 5 and h of 4? So here it is given m is equal to 6 and h or h r2 pi by 6k is also given 1 1 0.6 0 0 and 0. Okay, so already you have seen in the previous slides in the formula alpha, here alpha is equal to 0, right, and it is a symmetric sample. So g of k is equal to minus 1 to the power k hr 2 pi by 6 or n k, right, it is a hr. Right, r, right, and how we find out the values of h of n, we will get 1 by n g of 0, here m is even, so g of 0 plus 2, I will write up here 2 summation k is equal to 0 to u gk, then here I am writing cos 2 pi k by n plus 1 by 2, right? And how we will find out u? If u is odd, then n minus 1 by 2, and if m or n is even, then n by 2 minus 1. Here m is even, then we will find 6 by 2 minus 1. How much it is? 2, right? 3 minus 1, that is 2. Okay, now we need to find out first the g values, otherwise we can't put here. First we need to find out g of k or g of 0. If we put g of 0, then what we will get? Minus 1 to the power 0 hr. If we put 0 here in whole function, that you will get what is minus 1 to the power 0, that is 1 only you will get. Okay, then g of 1 minus 1 to the power 1, put in this equation. I am putting in this equation. Okay, minus 1 to the power 1 hr 2 pi by 6. Okay, or you can read hr 1. So from here, if you see the value of hr1, that you will get 1, and multiplied by minus 1 to the power 1 minus 1, right? Here k varies 0, 1, 2, 3 till m minus 1. Now g of 2 minus 1 to the power 2, we can directly h of 2. Yes, 2 pi by 6 is given, so 0, 1, 2. So what we will get at 2, it is 0.6, value is 0.6, minus 1 to the power 2, then we will get 1 only. So g of 2 value is 0.6, right? Okay, now here we got u, that is equal to 2, and g of 0, 1 and 2 values. Now we need to put in this equation in order to find out h of 0, h of 1, h of 5 and h of 4. Okay, so I am erasing from here. I hope all of you have noted down. Then we can solve these other values. Just we need to remember these points. Okay, now we need to take first h of 0. So here we are putting n is equal to 0 in order to find out h of 0. So here n is given 1 by 6, right? You can take it m, because here the m or n is equal. Okay, g of 0 plus 2, k varies 0 to u we got 2, g of k cos 2 pi k by 6, n is equal to 6. Here n plus 1 by 2 is there, so n is 0, so 1 by 2 only, right? Now 1 by 6, put all the values of g of 0 and solve this summation part. So g of 0 we got 1, 1 plus 2 in bracket. First we need to solve this summation. So if we are putting k is equal to 0, so g of 0 we got how much we got? 1, right? 1, then multiplied by cos 2 pi k by 6. Here k is 0, so cos 0, what is the value of cos 0? Cos 0 and multiplied by 1 by 2, so cos 0 only. To 1 plus g of 0 cos 1. Now we need to put k is equal to 1, k varies 0 to 2, right? So now g of 1, here I have written directly g of 0 in place of g of 0, the value. First we need to solve this, then we will write cos, otherwise we will confuse, 2 pi by 6. Here k is equal to 1, so k is 1, 2 pi by 6 into 1 by 2. Plus g of 2 cos 2 pi, here k is equal to 2 multiplied by 2 by 6 into 1 by 2, right? Now 1 by 6, 1 plus 2, 1 plus, what is the value of g of 1? That is 1. 1 multiplied by 2 to cancel, pi by 6, cos pi by 6. What is the value of cos pi by 6? Can anyone answer? Or you are solving? Are you solving this question? So okay, that is cos pi by 6 into cos pi by 6. Then we will put the g of 2. What is the g of 2 is given 0.6. That is 0.6. 2 and 2 will be cancelled. That is cos pi by 3. Right? Okay, already I have solved this. You can get the values of cos pi by 6 and cos pi by 3. 1 plus 2. Here I am multiplying. And then calculate the values cos pi by 6, that is 80 cos 30. Cos 30 value 1 by 2. So yeah, 1 by root 2. Yeah. So you will get, I think, 1.732. You can calculate it. I already calculated 0.6. Then if you add and divide, you will get 0.3113. Okay. If you add and then divide by this, 3.6 minus 1.732. That's why I suggested in the previous classes also, keep one calculator with you so that you can calculate it. Okay. So h of 0 you will get 0.3113. Now we need to find out h of 1, h of 5 and h of 4 also. Similarly, we need to calculate these points. Okay. Okay, so don't have other slide. So I'm erasing this, then I'm solving in this slide also. Okay. I hope all of you have gone. Have you got this question? Anyone have any doubt in this question? Can I erase it? Okay, I'm erasing this one. I hope all of you noted down. Okay, here it is g of k cos 2 pi k by n and n 1 plus 1 by 2, right? Okay, now we got h of 0. Now we need to solve for h of 1. So put all the values in place of n, small n 1, and for capital N, that is 6. It is given here. So g of 0 plus, after that I am writing here, so k varies 0 to u, we got 2, g of k cos 2 pi k by 6, and here n is 1, so 1 plus 1 by 2, what we will get? 3 by 2, right? So I am writing here directly 3 by 2. Now we will solve for the summation. G of 0, what is the value of g of 0? We got 1, right? 1 plus 2 in brackets. Now we need to solve this summation. Put k is equal to 0, 1 and 2 in this summation. So when we are putting g of 0, the whole part will be the cos 0. So cos 0 is 1. So g of 0 I am only writing. Then g of 1, k is equal to 1, so 2 pi by 6. Sorry, cos 2 pi by 6. Cos 2 pi by 6 into 3 by 2 plus g of 2 cos 2 pi by 6 into k is 2 here, so 2 pi into 2 into 3 by 2, right? Now 1 by 6, 1 plus 2, here g of 0 is given, that is 1, and g of 1 is also 1. We got g of 1 is minus 1 is there, so that's why we got minus. G of 1 is minus 1. Here 2 cancel, 3 cos pi by 2. What is the value of cos pi by 2? That is 0, right? Cos pi by 2 value is 0. Then g of 2 is 0.6. Here we will solve this. 2 cancel, 3 here. So only cos pi is left. Then what is the value of cos pi? I think that is minus 1, right? So 1 by 6 in bracket 1 plus, here this part is 0, so 2 if multiplied in the 2 minus 1.2 if you multiply this. Okay, so 3 minus 1.2, that we will get 1.8 by 6, we will get 0.3, right? Okay, so now here it is given the unit sample response is symmetric and m is 6. So if m is 6 means it is even number of samples are there. So we know that for symmetric unit response function, h of 0 must be equal to h of 5 and h of 1 must be equal to h of 4 and h of 2 must be equal to h of 3. So total number of samples how much? 6, right? H of 0 must be equal to h of 5, h of 1 must be equal to h of 4 and h of 2 must be equal to h of 3. So here we have taken the h of 0 and h of 1 value. So h of 0 value is equal to the h of 5 value. So what will be the h of, here we got 0.3113 and h of 1 we got 0.3. So h of 1 is equal to h of 4, then 0.3. So we need to just, in this question, if there is a symmetric unit sample response and n is odd, so we need to find out only two values, that is h of 0 and h of 1, and then we need to apply the symmetricity property in this. H of 0 must be equal to h of 5 and h of 1 is equal to h of 4, then thus we get these values. So I'm removing from here, then writing it. Okay, so h of 0 must be equal to h of 5 and h of 1 for a symmetric unit sample response. H of 1 is equal to h of 4 and h of 0 we got 0.3113 and h of 1 we got 0.3, that is equal to h of 5 and it is equal to h of 4. Okay, so from here you can solve this question like this. Okay, have you got this question how to solve? Okay, moving to the next question then. So the next question is, an ideal low pass filter with frequency response characteristic h of omega as in equation is given as in equation number 3, where omega c is the cutoff frequency. If the impulse response of a filter is h of n and h of 0 is equal to 0.6, then determine the value of omega c. So here it is given h of 0 is equal to 0.6 and we need to find out the cutoff frequency of the impulse response of the filter, that is h of n. So in order to find out the cutoff frequency of a filter, it is given, formula is given h of 0 multiplied fs by 2. This is a formula to find out the cutoff frequency of the filter. If it is a low pass, h of 0 is given, that is 0.6, and here the sampling frequency is not given, we can take 10 kilohertz. Assume the sampling frequency is 10 kilohertz or it is given somewhere. Okay, and in this question it is not given, or the question it is not, but the sampling frequency is 10 kilohertz. Okay, assume that. So the cutoff frequency is 0.3 into 10 to the power 3, we will get is 3 kilohertz. Okay, so if this type of question is given, an ideal low pass filter with frequency response character h of omega, and this is given like it is a low pass filter and omega c is the cutoff frequency and impulse response, that is h of 0, is given at one point, then how we will get the cutoff frequency? Then in order to calculate the cutoff frequency, this formula is applicable. That is cutoff frequency h of 0 fs divided by 2. And if fs is given, then put it. If fs is not given, then take it as a 10 kilohertz. Okay. This is applicable for only low pass filter. We will see the question during the lectures. Okay, I will say that, then I will let you know. Okay, what are the cutoff frequencies for other filters. Okay, moving to the next question then. H of n is an anti-symmetric unit sample response of a linear phase FIR filter. If the order of the filter is 87, then determine the number of filter coefficients that specify the frequency response. Here, the order of the filter is given, that is 87, and 87 is odd number. And also it is given the h of n is anti-symmetric unit sample response. So for anti-symmetric unit sample response, how we will get the filter coefficient? So number of filter coefficients for anti-symmetric, number of filter coefficients in anti-symmetric unit sample response linear FIR filter. I'm not writing all those things. The formula is, you know, that m minus 1 divided by 2. Here m is given, that is odd, then it is m minus 1 divided by 2. If m is even, then m by 2, right? 87 minus 1 divided by 2, that is 86 divided by 2, that we will get 43. Okay, so the correct option is option B. Okay, here it is given h of n is anti-symmetric unit sample response and linear phase FIR filter, and order of the filter is 87, that is odd. Then determine the number of filter coefficients that specify the frequency response. Okay, so number of filter coefficients in an anti-symmetric linear phase FIR filter, the number of coefficients will be m minus 1 divided by 2. Okay. Okay, moving to the next question. Which of the following are the advantages of FIR filter over IIR filter? Option A, can be designed with exact linear phase. Option B, filter structure always stable. Option C, computationally more efficient. So I hope all of you have gone through the lecture videos. So option A and option B is correct. Can be designed with exact linear phase. FIR filters are designed with exact linear phase, and the filter structure is always stable because it is a finite number of filters. It is a finite impulse response, so n is defined. So that can be a stable number. Okay. Okay, moving to the next question. The roots of a polynomial h of z are identical to the roots of the polynomial h of z inverse. It is true or false? Can you participate in this type of questions? Can you answer in the chat box, please? The roots of the polynomial h of z are identical to the roots of the polynomial h of z inverse. It is true or false? So already we know that the linear phase FIR filter is at z to the power m minus 1 h of z inverse is equal to plus minus h of z. We have also solved this problem. So this result implies the roots of the polynomial h of z is identical to the roots of the polynomial h of z inverse. Already told you, h of n, the linear FIR filter must follow this linear phase property, n minus 1 minus n. So if we take z transform of this, then multiply z inverse, change z to z inverse and multiply it with the z to the power m minus n, then we will get the same. Okay. So the roots of the polynomial h of z are identical to the roots of the polynomial h of z inverse. That is true. Okay. Moving to the next question. So the next question is, which of the following window is used in the design of the low pass filter to have a frequency response as shown in the figure? So this is the frequency response of a filter, of any filter. Can you see and answer in the chat box which window function frequency response is this? The low pass filter frequency response is this. Option A is Hamming window, option B is Hanning window, option C is Kaiser window, and option D is Blackman window. So this is the frequency response of a Kaiser window. You can see in the slide, or already you have gone to the NPTEL video lecture, or you can get it from here. So there are some window functions which I have discussed in the class and their transition bandwidth and their frequency response. I think so. This is a frequency response of a Kaiser window. Okay. Yeah, someone is. Okay. Yeah. Okay, so option C is the correct answer. So this is a frequency response of a Kaiser window. Okay, moving to the next question. In the frequency sampling method for FIR filter design, please specify the desired frequency response that is misplaced. HD of omega at a set of equally spaced frequencies. It is true or false? So the question is given in the frequency sampling method. For FIR filter design, we specify the desired frequency response SD of omega at set of equally spaced frequencies. In the frequency response sampling method, you have seen that we specify the frequency response SD of omega at a set of equally spaced frequency, that is omega k is equal to 2 pi by m k by k plus alpha, right? So we put the frequency in this order. So omega k equal to 2 pi by m k plus alpha. Alpha can be 0 or 1 by 2 or any other value also, and k varies from 0 to n minus 1 or m minus 1. So at this, so this is the true. In the frequency sampling method for FIR filter design, we specify the desired frequency response C omega at a set of equally spaced frequency. That is true. Okay. Okay. So moving to the next question. Consider system equation y is equal to n plus 2 is equal to minus 3xn plus 2 plus 2xn minus 5xn minus n. The system is dashed and dashed respectively. That option A is non-causal or IIR filter. Option B is causal IIR filter. Option C is non-causal FIR filter, and option D or option 4 is causal FIR filter. So the system equation is given, that is y n plus 2 is equal to minus 3 x n plus 2 plus 2xn minus 5x n minus 1. So in order to solve any question or problem, we just first need to take the Z transform of this function in order to find out whether the system is causal or non-causal FIR or IR filter. So first we need to take the Z transform, that is the Z transform of this equation is Z to the power 2 y of Z is equal to minus 3 Z to the power 2 x of Z plus 2x of Z minus Z inverse x of Z. Now we need to find out the transfer function, that is transfer h of Z or impulse response. The impulse response is defined by y of Z divided by x of Z, right? So now first take common x of Z in bracket minus 3 Z to the power 2 plus 2 minus 5 Z inverse, right? Let's find out the Z impulse. In order to find out the impulse response or h of Z, that is equal to minus 3 Z square plus 2 minus 5 Z inverse divided by Z square, right? So now from this equation you can see that this is a all zero system, right? Here the poles are 0. At 2 points the poles are 0. So if we divide in numerator and denominator by Z square, then what we will get? We will get minus 3 plus 2Z inverse minus 5 Z to the power minus 3, and here only, right? Are you getting this? So the transfer function does not include any positive powers. See here minus 3 plus 2Z inverse minus 5Z to the power minus 3. And order of the numerator is also not exceeding the order of the denominator. So system is finite impulse response and causal, right? If we find out the poles are inside the vector. So system is causal and FIR filter, finite impulse response. Okay. Okay. So I hope all of you got this question. So we can move to the next question. Okay. So the next question is, design a low pass filter with pass band edge frequency is 0.2 pi and stop band edge frequency is 0.3 pi, where pass band ripple is equal to 0.01 dB and stop band ripple equal 0.01 dB. Sampling frequency is 16 kilohertz. Here sampling frequency is given. What we need to do? We design a low pass filter, right? So what are the parameters required to design any filter? Already told you. We need a pass band frequency, stop band frequency, pass band ripple and stop band ripple, and transition bandwidth. These are the main parameters which are required to design any filter. So now first see what are the parameters are given. So pass band edge frequency is given, that is 0.2 pi. Stop band edge frequency is also given, that is 0.3 pi. Pass band ripple and stop band ripples are given, that is 0.01. Del P is equal to del S, 0.01 dB. So now first we need to find out the magnitude or or ripple, attenuated ripple of that pass band, stop band. So how we will get it? Let's represent by del 2. It is minus 20 log, already you have seen in the slides, 10 del s, right? And it is given 0.01. So if you solve this, 20 log 10, 0.01, how much you will get? Minus 20 log 10, it is 10 to the power minus 2, right? If you take, you will get 40 dV, right? So the stop band ripple is 40 dV. What is the main lobe width or transition bandwidth? You can say that of that the frequency response of a low pass filter. You have seen that is a main lobe width can be defined omega s minus omega p, or normalized transition bandwidth, that is minus omega s minus omega p. So omega s is given 0.3 pi and omega p is given 0.2 pi. From here we will get 0.1 pi. Now we need to get the transition bandwidth. So we can get from the window method, window Fourier series method, or frequency sampling method. So easiest way to find out the transition bandwidth. So choose any one window function or window method in order to find out the transition bandwidth or the order of the filter. So here I am choosing the Hamming window. So what is the transition bandwidth for the Hamming window? That is given del of omega, or you can represent it by that del, what transition bandwidth of this is 8 pi by m. We know that, and here the main lobe width is given for the low pass filter. We have find out 0.1 pi. In order to find out the order of the filter, it must be a equal 0.1 pi, right? So pi and pi will be cancelled, m we will get 80. Okay. So if this type of questions are given, where pass band and frequency, stop band and frequency, and pass band ripple and stop band ripple are given, now we need to design a low pass filter. So these are the basic specification or basic parameters of filter design which are given. If it is not given, we need to find out. Okay. So in the most of the cases it is given. So from here we need to find out the attenuated ripple of pass band or stop band, and the transition bandwidth, or what is it, main low width. And from here, after that, we need to select any window function with that. And from here, already it is given the transition bandwidth of every window function. For rectangular window, it is 4 pi by m. A Hamming for and Bartlett filter, it is 8 pi by m. So compare with this, and you will get the order of that filter. What is the order of the filter? In most of the cases, the order of the filter is only asked. Okay. You can choose any window. You can choose any window. It depends. So you have to write in the question. So you are choosing that rectangular window or Hamming window or Hamming window. Okay. So moving to the next question. Which of the following window is used in the design of a low pass filter to have frequency response as shown in the figure? That is option A, Hamming window, option B is Handling window, option C is Kaiser window, and option D is Blackman window. So if this type of question is given, you have to remember that frequency response of every window function. So this frequency response is a Blackman window. So option D is the correct answer. So this is the frequency response or loop of a Blackman window. So option D is the correct answer. Just you need to remember the frequency response of every window function. Okay, for this type of question. Okay, moving to the next question. So next question is, consider a 51 tap linear phase FIR filter operating at sampling frequency of 10 kHz. The delay of this linear phase FIR filter is, here the n is given 51. Consider a 51 type linear phase FIR filter operating sampling frequency at 10 kHz, and sampling frequency is also given, that is 10 kHz. So how you will find out the delay of this linear phase filter? So if this type of question is given, so in order to calculate the delay of a linear FIR filter, so for FIR filter, which has n tap linear phase, then in order to find out the delay, the formula is n minus 1 divided by 2fs. Okay, if any function or any FIR filter is given and their order is given, sampling frequency is given, so delay associated with that FIR filter is calculated by n minus 1 divided by 2fs. So there is 51 minus 1 divided by 2 multiplied by 10 kilohertz, 10 into 10 to the power 3. That is 50 into 20 10 to the power 3. So 0 0 cancel. 2.5, that is 2.5 millisecond delay associated with linear phase FIR filter. So option D is the correct answer. Okay. Okay, so have you got this question? We can move to the next question. Okay, moving to the next question. Consider an FIR filter whose impulse response is h of n is equal to k varies from 0 to 6, and in brackets here it must be h of 4 minus mod of k minus 3 del n minus k. The phase function of h of n is, what will be the phase function? Here k varies 0 to 6, that means the order of this function is 7, right? 0 to 6, and if it vary from k is equal to 0 to 6, 0 1 2 6, so it must be symmetric at k over the k is equal to 3, right? So h of 0 must be equal to h of 6, and h of 1 must be equal to h of 5. H of 2, that is h of 2 must be equal to h of 4, and h of 3, so at k is equal to 3, and at k is equal to 3, at over it must be, these values must be from h of 3 equal to the h of 3, right? So now first we need to find out the values of h of in order to find out the phase function of h of n. then first we need to put the values of k here and find out the, or similarly we can find out the z transform of that function also. So h of n, or if we are taking the z transform of, we can put z transform or putting the k values also. So we are doing the both tasks similarly. So h of z is h of 0, right? We are putting k is equal to 0. Here the 4 minus 3, 1 only, del to the power n minus 0, right? So it is del, it is h of 0 only. Then if we put h of k is equal to 0, or h of 2, so if we put k is equal to 0, then we will get k is equal to 0, we have put in k is equal to 1, so 1 minus 3 minus 2 in the mod, so 4 minus 2, 2 only, right? 2 z to the power minus 2, n minus 2, okay? So 2 h of 2 here left, plus similarly we can find out 3 at hk is equal to 3, we will get h of 1, then h of 2 to the power z to the power minus 2, z to the power minus 1. We have put it first h of k is equal to 0, 1, 2, 3, 4, 5, 6. We have to move like this. Then here we will get like del n minus k. So if we put 1, then z inverse. If we put k is equal to 2, z to the power minus 2, something like z to the power minus 6. Okay, if you solve this. So I am writing here the values 3, then we will get 4 h of 3 when we are putting k is equal to 3, z to the power minus 3. Then if you put k is equal to 4, now what we will get, 4 minus 3, 1, okay, 4 minus 1 is 3. Then again we are coming to this h of 4 z to the power minus 4 plus 2 h of 5 z to the power minus 5 plus again 1. If you put 6, 6 minus 3, 3, 3, 4 minus 3 is 1. So you will get 1 h of 6 z to the power minus 6. So from here you can also see that the magnitude is also equal. H of 0 is equal to h of 6, h of 1, h of 5, that is 2 and 2, 3 and 3, h of 2 is equal to h of 4, and here only h of 3 left. Okay, so after finding out this, if it is written in terms of the frequency response term, so we will get only h of 3 is left, right? You have seen, and h of 0 is equal to h of 6, and h of 1 is equal to h of 5, h of 2 is equal to h of 4. So you have seen that. So how we can write in the compact form or in the frequency response term? So e to the power minus 3 j omega, right? Only because only this part is left and all other parts are equal. So by taking common, you can solve this type of question in the, I think, in the previous case where linear phase FIR filters are required, or in the previous slides of signal and system. H of 3 plus here n varies 0 to 2, 2hn cos omega n minus 3. Okay, so here this term denotes the phase. So phase is minus 3 omega. Okay, so first just we need to put the values of k is equal to 0 to 6, and here from where just we are seeing that h of 0 is equal to the h of 6, h of 1 is equal to h of 5, and h of 4 is 2 is equal to h of 4, and h of 3 is only left. So we take it out that part, and it is equal, so n varies from 0 to 2, and h of 3 is common, and we write it in terms of h of n and cos omega n minus 3. Okay, so from here you can get the phase, that is minus 3 of omega. Okay, have you got? Yeah. Hmm. In the which? Hmm. Okay, I think that is a minus in minus in there. Because that is the plus minus h of n must be equal to the minus h of n minus 1. I think from here we need to solve it slowly. I will confirm you in the next class. Okay. But most probably it is a minus. It must be a minus. Yes. Oh, yeah, yeah. Okay, okay, sure. Okay, so moving to the next question. Design a low pass filter with pass band F, that is Fp is equal to 2 kilohertz, and stop band frequency Fs is equal to 2.5 kilohertz with attenuation of at least 40 dB. Let the sampling frequency f of s is 10 kilohertz. Using the technique you know, determine the design with the least number of coefficients. So here we need to design a filter with least number of coefficients. Here the pass band frequency, stop band frequency is given, sampling frequency is given, and attenuation is given 40 dB. So it is given in kilohertz. So in order to find out the normalized pass band frequency and stop band frequency, how we will get? Already you know that what is the normalized pass band and stop band frequency is represented as, the normalized pass band frequency is represented as omega p, and normalized stop band frequency is represented by omega s. So how you will find out? Already you have seen that in the first lecture in the conversion part, that is given by Ft divided by Fs, right? In order to find out the passband, normalized passband frequency. So 2 pi Fp is given 2 kilohertz and Fs is given 10 kilohertz. So kilohertz will be cancelled. So 2 by 10 I am writing. So what we will get? 2 pi by 5. Normalized stop band pass band frequency. Similarly, we will get normalized stop band frequency, that is 2 pi fs, that is capital S, divided by f of s. So 2 pi into 2.5 divided by 10. So from here we will get pi by 2, right? So what is a transition bandwidth or width of the main lobe? That it represented as del of omega, that is omega s minus omega p, right? You have seen that frequency response of low pass filter in the very first slide. So just remember that frequency response, that is very important in order to find out omega s, omega p, del p and del s. Okay, so that is pi by 2 minus 2 pi by 5. From here you will get how much? Pi by 10, right? Yeah, pi by 10. So in order to find out the order, we need to choose any window function. So you can choose, if it is not given, you can choose or specify that I am choosing this window function and then find out the order of the filter, or if it is given then take. So here I am taking the Hanning window function. So what is the transition bandwidth of a Hanning window function? You know that is 8 pi by m, where m is the order of the filter, and here it is a transition bandwidth and this is a transition bandwidth of that filter which specification are given. So if we compare that, or in order to find out the order, just equal to the that one, so pi and pi will be cancelled and we will get equal to 80. Here you can choose any window function because it is not given. You can choose the rectangular window function also. If it is a rectangular window function, then what is the transition bandwidth for rectangular window function? That is a 4 pi by m, right? For Hanning window function. If it is a rectangular window function, so we will get pi by 10 is equal to 4 pi by m. Pi and pi will be cancelled. From here we will get order of the filter is 40. Okay, so it depends on which window you will choose. If it is not given, you can choose and mention that I am choosing this window function, and if it is given, then calculate it. Okay. Okay, so moving to the next question. Design a discrete time low pass filter for a white signal. The specifications are given. The passband frequency Ft is given, that is 4 kHz with 0.8 dB ripple. Okay, that is alpha p, that means given. Stop band frequency Fs is 4.5 kHz with 50 dB attenuation is given, that is alpha s. If you have seen in that frequency response curve, you will understand that. Okay, sampling frequency is given 22 kHz. Then what we need to determine the discrete time passband and stop band frequencies, or we can see that normalized passband and stop band frequencies, the maximum and minimum of h of omega in the passband and stop band, where h of omega is the filter frequency response. So what we need to find out, what are the specifications are given, what other parameters we need to define, or we can get, that is omega s, omega p, that is a normalized passband and stop band frequencies. Then we need to find out the maximum minimum values of h of omega in the passband and stop band, that is alpha p and alpha s. Okay, no, that is del p and del a, maximum minimum values of h omega. Okay, now how we can find out these values? So as we know that in order to find out any omega p, already discussed in the previous question, that is Fp divided by Fs in order to find out the normalized distal passband frequency. That is 2 pi Fp is given 4 kilohertz and sampling frequency is given 22 kilohertz. So kilohertz will be cancelled, so 4 by 22. So what we will get from here? Anyone of you want to calculate? 4 by 11 pi. Okay, 4 by 11 pi, that will be equal to 0.36 pi, right? If you calculate 0.36 pi. Similarly, we need to find out the omega s, that is 2 pi f s multiplied by fs. We will get 2 pi multiplied by 4.5 kilohertz divided by 22, right? So when you solve this, you will get 0.41 pi, and it is represented in radians. You know, omega is represented radian per second. So we know that the maximum maximum minimum values vary in the passband 1 minus del p to 1 plus del p, right? You know that is very, and in order to find out 1 plus minus del, so already you have gone through the formula in order to find out the maximum or minimum passband values, that is 10 1 plus del is equal to the passband ripple is given 0.8 dB. Okay, so if you solve this, you will get log 10 1 plus del is equal to if you solve with 0.8 divided by 20, that you will get 0.04. Okay, and you solve this log question problem. So 1 plus del is equal to 10 to the power 0.04, 10 to the power 0.04, and in order to find out del, 10 to the power 0.04 minus 1, right? You will get 0.096. Please calculate with the calculator. Okay, so it vary 1 minus del p to 1 plus del p. So 1 minus del p, you will get 0.9035, and 1 plus del p, you will get 1.096, right? So the maximum and minimum value of the passband is 0.9035 and 1.096, and similarly we need to calculate what is the value of stop band ripple. Okay, so already it is given, so I am going to remove this part. Okay, I think you can note down. Okay, similarly we need to calculate the in the stop band value. So how we will get 20 log, in the stop band only one is there, one value is there, you can represent a del s is equal to 50 dB is given, right? Here minus 20 log del of s. So log 10 is there, log 10 del s 50 by 20 minus 50 by 20. So del of s will get 10 to the power minus 5.2, right? When you solve this, you will get 0.0 0.03. Okay. So in the stop band, the value of h of omega is 0.003. Okay. So these are the parameters what we need to determine the normalized or discrete time pass band and stop band frequencies, maximum and minimum value of h of omega in the pass band and stop band. So maximum and minimum value is in the pass band it is, and in the stop band value is 0.03, and already we have determined the discrete time pass band and stop band frequencies. So can I write it clearly somewhere? Okay. I am writing it here, the answer. Answer A is discrete time pass band and stop band frequencies are 0.365 and stop band frequency, that is omega f, is omega s is 0.41 pi. It is represented in radian per second. Okay. Maximum and minimum value of pass band something is going on. It is not responding, just a minute. Value in pass band is hello. Uh, I am audible. Are you able to listen? Hello. Yeah, I thought the time get disconnected. So already I had written there the discrete time pass band and the stop band frequency, that is 0.365 and the stop band is 0.415. Currently I'm not able to write it here, something is going on. So maximum values of the pass band is 0.096 or 1.0.096, 0.90. Maximum minimum value in the pass band is 0.09035, 0.9035, and for the stop band the value of that is 0.0031. Okay. So already I have written, you can see In the previous one, currently I'm not able to write, or I thought that I will summarize it here. Okay. So these are the questions for this week. Anyone of you have any doubt, you can ask now. Otherwise, we can close the session. So thank you everyone for joining. You can ask the questions now. Okay, hello.